All right, good. So today's goal is to talk about string algorithms. And here's the basic problem. You're given a large text, and you have a small pattern, and you want to find occurrences of this pattern in that text. That's okay.
Just sharing the link.
Yeah. So typical examples are what happens when you open Microsoft Word and you're trying to search for something. Typically, you're searching for small words, and the text may be much larger than the pattern. So you assume here that the pattern is much smaller than the text, and there are various kinds of problems that one wants to ask, and I'll show you that in a second. Here are possible questions. So the first question might be, does the pattern even occur in the text? Find me one occurrence, I don't care which one, or find me all occurrences of this pattern, or count how many times this shows up, or if this pattern is not completely there, find me some parts of it that might be there, or find me an approximate thing. It doesn't have to be exact. Maybe maybe I misspelled the word, or maybe the word is misspelled in the document and I'm searching for it, right? Or what if I want to look for repeats? And repeats are also quite interesting. So some of these problems come from DNA sequence analysis, where in the human genome, for instance, there are lots of these repeats, and you want to find repeats, and you don't care. So you're not really searching for something specific. You're just saying, find me repeats. Or this one is also quite interesting, where often you don't find the whole thing that you're searching for, but you might just find a part of it. So these are all various problems, and you can have many more variants, it turns out. These are not the only ones. You could ask, okay, find me all occurrences of the pattern P, but maybe with 2 or 3 mistakes, or at most 3 mistakes. So I can make the problem as hard and as interesting as I want. And in each case, it looks like a different problem, but in all of these problems, we want to figure out some basics that we can apply in as many of these problems as possible. So today's goal is not to solve any specific problem from VJudge or whatever, but to try and understand some of this theory so that you guys can use this in many string-related problems. Now, in terms of the algorithms in the literature, there are way too many. There's a gazillion of these. The first one is the brute force one, the naive method, which is what you and I would do if we didn't know any other algorithms. And then there are so many more. We're not going to look at all of these, but I'll try and give you a flavor of many of these. Okay? All right, so let's start with the first one, the brute force. The naive strategy goes something like this. Assume that this is a large text that I want to search. I've just put a bunch of characters, but it's not so hard to imagine. And let's say I want to look for the word ananas in this text. So the naive strategy says, go align it with the leftmost thing and compare. So A matches with A, N doesn't match with T, so that's not the right occurrence. So what are we going to do? We're going to slide this over by 1 position and restart the whole process. This time A doesn't match with the T, so immediately you know, okay, time to move this. Now A matches, but again N doesn't match. So you keep doing this, and here's your first occurrence. You could stop here if you only wanted to find any occurrence or the first occurrence, but if you want to find all occurrences, then you would have to run through the whole sequence, and eventually you'll find some of these other things that look close enough or whatever, and you potentially are capable of finding all occurrences of this pattern in the text, right? This is naive, this is simple. You can write this code in about three statements or so, couple of for loops, and you're done. But what's wrong with it? Well, what's wrong with it is it's not terribly efficient. How bad is it? Well, if the text is of length n, and if the pattern is of length m, then the time complexity, the worst case time complexity, is going to be n times m. You could also think of the worst case scenario. Let me borrow a pen. Oh, thank you. So let's think about the worst case. What would be an example where it would perform really, really poorly? Any thoughts on this?
Maybe like you said, like if our pattern is like really large or really long, I guess like you said, it wouldn't. I guess the running time like would be like really long. I guess, yeah.
There are better worst cases. So let me see if Lazaro has some thoughts on this.
Is it when the text it matches both the first letters of the pattern except the last one? And that's what
right. So the worst case is going to be I match this, and then right at the end it fails. Right? And then I move it over, and again the same thing happens. How could that happen? What kind of example would that be? Even after I move, I still want everything matching except the last one. And I want this to happen all the way to the end. That would be the worst case, right?
Yeah.
It's pretty clear.
But once you shift it?
Yeah, once you shift it, it still has to match everything except the last one. The only way that can happen is if this part here is the same as this part here, right?
Yeah.
So here's an easy example. I make all of these as A's. And I make this guy as all A's except the last one. Right?
Yeah.
Easy, right? So in this case, what would happen is all of this would match, and it would have a mismatch at the last character. I would move it. Again, it would match all the characters except the last one. It'll keep happening. If you want, you can make this last guy a B, and you'll find a hit at the end or not. Doesn't really matter. But the worst case has been achieved. This is what would mess you up. So if you have simple texts, which is not uncommon, or simple patterns, you could really mess up. So you want to avoid this. You don't want to have this kind of a poor worst case. And it doesn't have to be this bad. You could still make it pretty bad by putting the B somewhere in between, somewhere at midpoint. Even then, it would compare half the characters every time. So we need something else, right? Okay. So here, what you have to notice is that
Professor, sorry, when you say half the characters, like, yeah, like...
Yeah,
what
forget that comment. Forget that comment. Yeah, that wasn't very, not very useful. It'll only confuse you. Just forget that, okay?
Oh, okay, and just to recap, the running time of this algorithm, like how
Yeah.
we came up with it is basically the length of like the string we're trying to match times the length of the entire thing, right? That's basically what it is.
Yeah, so for that you have to think of the code. Yeah, this is, all right, so you're going to say for I equals 1 to n, where n is the length of text, right?
Okay.
For j equals 1 to m, where this is the length of p, of the pattern, right?
Ah, okay, Okay.
And then I'm going to say if text sub I is not equal to pattern sub j, what do I do?
If it's not equal, we break.
We break. So that means we're going to, just hit break. That's it.
Okay,
right?
okay, all right.
So clearly it's n times n.
Right, okay, okay.
Right? That's the time complexity. Pretty clear, right?
Right, right.
Okay, good. So we want to improve on this. This is terrible. Especially if the pattern is long, this is going to be quite painful. So here we have to notice a few things. The fact that I matched all of this and then I had a mismatch here. When I moved this over, I already knew they were all A's, but yet I went and matched them again. So I wasn't very smart when I did the brute force thing. Because if somehow I knew that these were all matched and they were the same, I could somehow improve it. But the problem is I don't know how to do that. Okay? So that's what we're going to try and figure out. Is this making sense?
Yeah.
So there are a bunch of things here that already matched. We just are not using that information. Here's, yeah, right. So how do I use that? Well, in order to understand that, we're going to look at a completely different approach. And then we'll come back and see how to improve this. All right? Any thoughts, any comments, Lazaro?
No,
You're still thinking about what I said.
Yeah, but they went over it in the Computer Programming 3 book.
Uh-huh.
Like, where they did keep track of the indexes of the
Yes.
previous matching.
Yes.
So when they do shift, they don't have to start from the beginning.
Correct.
Pick it up from where
Yeah.
they
So
started.
that's what we're going to somehow use. So in order to understand that, we have to go back and look at something called finite state automaton. Either of you have seen this before?
No.
Neither of you. Okay, fine. That's fine. Eventually, before you graduate from computer science, you would have seen it because it's required material. It's in the class, and you'll see that. So let's look at this example with Ananas. Okay, I'm going to build a machine, or I'm going to describe a machine which remembers some things. So this is going to be a little bit strange, but let's bear with me. Hopefully it'll make sense soon. When I started, let's say that I haven't seen anything so far. If I do match an A, then I've matched a part of the word ananas, right?
Okay.
So I'm going to remember that I've matched the first letter. So I am going to go from state 1 to state 2. By saying I'm now in state 2, I'm saying, oh yeah, I've seen the A before. Then at state 2, if I see an N, I can tell myself, oh yeah, I've now matched A, N. So let me remember that, and let me put down my state as state 3. So my state number tells me how many of the previous characters were exactly the same as what it should be. Good?
Okay.
So therefore, this is what the system is going to look like. If I see an A when I'm in state 1, I'll go to state 2. If I see an N in state 2, I'll go there, and so on and so forth. If I get here, then I have matched the entire word, and I can report this. So I'm going to call this as the start state and this as the end state. If I ever reach the end state, then I will report. Okay. However, the problem is that I might match part of it and end up with a mismatch. Well, what happens if in state 1 I don't see an A? If, or let's say in state, well actually I'm starting somewhere at the end, doesn't matter. Okay, let's say in state 6 I see an A. That means I've already seen A, N, and then A followed by another A. That means my word is all completely messed up, but I can use that last A to say, oh yeah, maybe this is the start of the word ananas. And so instead of going to state 1, I'll go to state 2. That's an improvement, right? There are more such things I can do. If in state 2 I keep getting A's, I could stay there. So if it's A, and then an ananas, maybe it'll come, maybe not, but at least I'll stay in state 2 and say that I've seen the A already. Okay. Here's another one. If in state 4 I see an A, I could go to state 2. So regardless of where, it seems that either in state 2, 4, or 6, if I see an A, I go to state 2. Because that's what it seems like here. All right? Here are some more. What if in state 6, I see another N? Now, instead of the S, I'm seeing an N. That means that I already have AN, AN, AN. So I can skip the first two ANs, right? And then now I have AN, AN, AN. I need to look for AS at the end, and then I would have the match. Did I make sense? I lost you somewhere.
Okay, yeah, maybe I somewhat, or I don't completely I don't completely understand.
So, okay, so I can't. So what we're going to do is think of the state and understand what its description is. If I'm in state 3, I've already seen A followed by N prior to me.
Okay.
And I'm looking for the rest of the word.
Okay.
So if I'm here, what have I seen already? I've seen AN, AN, AN.
Okay.
AN, AN, and an A. I'm looking for the S now. But the S doesn't show up, the N shows up. So if I look at the previous part, I see that now I have an N, A, N, A. So that's AN, AN of the ananas word. So I have the 4 letters of the ananas word, so I go to state 5. Does that make sense? So
so basically you mean like the next, so like if you were at stage 6, but then the one after that didn't match, so you're going to start at stage 5 now?
Yeah, well, it's not just not match, it's the fact that it's an N. So you need to think about this, all right? Okay, so we can now, it turns out, do all the other possibilities and get a detailed machine, detailed set of transitions. I could put this into a table that says, if I see an A, I get to state 1. But if I'm in state 1 and I look and I see an N, I should go to state 2. If I'm in state 2 and I see another A, I should go to state 3. But if I see any of the others, it'll tell me what I should do. So these are all things. This table will tell me a complete description of where I'm going to go when I see what. This is going to help me not having to match things over and over again, because I have now recorded this information in a state which captures what my previous substring is. Okay? So state captures the previous substring, and that's roughly what it is. So in general, this is like
Professor, maybe basically I guess the idea is that like instead of like when we try to match our string, I guess instead of moving it like one position at a time, so like we don't necessarily have to.
Yeah.
Oh, okay.
Yeah. Well, it's yeah, that's actually correct. Yeah. So this gives me a broad set of strategies, which I'm going to call as sliding window strategies, where I have a window for the pattern and it moves. It moves when there is a mismatch, but this will tell me how much to slide it by. Okay, and that's the good part. So let's actually look at Ananas, because that was a good example, perhaps. So the pattern was Ananas, right? And some of the things that we were doing there. Well, so you can see what kind of things might happen. So if I see A-N-A, then I know that I've matched 3 of them. If I see an S here, I'm in trouble. Then I have to go back all the way to the start and restart the whole thing, which means if this is an S, I can slide this whole thing over to the right of S, right? So that's really great. On the other hand, if this were an A, then I could use the first A and nothing else. So I'm going to slide it so that it aligns with the A, and then the A I'm not going to match again because I'm going to get to state 2, so I already know that that's been matched. So if I can pre-record that information, then it helps me figure out how much to slide this by and to what state I should go to. Both these pieces of information get in, and that helps me to avoid redoing a lot of the checking. That's the secret of many of these string matching algorithms. All right. So we can use this state diagram kind of idea to figure out how much to slide things by, and and it'll also tell us that we don't have to rematch anything, almost. So here is the general plan. We're going to initialize the window on the text. So to start with, the text is going to be aligned with the leftmost point of the text. Pattern is going to be aligned to the leftmost point of the text. Then, as long as the window hasn't reached the right end, I am going to check each character in the pattern, match it with each character in the text, and then if that doesn't work, I'm going to shift it and continue. This is the brute force strategy. The only difference now is that I am going to figure out how much to shift the window by, and one more trick I'm going to do is I'm going to never go back to the start and recheck. I'm going to stay where I am and continue. So if the mismatch happened here in the text, I will move the pattern over, but I'm going to continue the text where I was. So I'm not going to go back and start the text from here, right? So even though I may only move it a little bit, I am never going to go back and check things over. That's the trick. So what about the other example we had, the worst case example? The worst case example had all A's, right? And the pattern had a bunch of A's followed by a B. What's going to happen here? It's going to match all of this, and there'll be a mismatch right there. Right? Now what? Well, I can't move it over by a whole lot. I can only move it over by 1 because I need to remember that 4 A's are still matched. But now I don't have to match all this over again. I just have to rematch this with it. So I'm staying in the same place in the text while sliding the pattern over by some amount. So in every match, either the pattern is going to slide over, or the pointer in the text is going to move over. One of the two is going to happen. Because of that, the time complexity of this algorithm is going to be m plus n. And that's because at every time, either I move the text pointer or the pattern pointer. Okay, so that's the nice thing about these types of algorithms. We haven't yet worked out the details, so that's what we're going to do next. Any questions about this so far? So general strategy is what we did with the brute force. The improvements are, we may end up sliding by a lot, but regardless of how much we slide it by, even if we slide it only by a small amount, we're never going to rematch things we have already matched. Because the sliding over is going to be such that everything that was already matched is going to be perfectly matched already after you have slid it over. Okay? So you will always slide it over just enough so that everything that was already matched is matched. Okay? So that's why over here I only moved it by 1, but I still don't have to match all this again. So therefore, every time I will just match a new character, and I'll just very quickly I'll come to the end and figure out that that's where it is. All right?
Can you just recap, so like the window pointer and the text pointer, so where are they?
Yeah. So pattern pointer is here, text pointer is there, and that's where it failed, right?
Okay.
Now what happens? After I move it here, I've slid it over. I now don't have to match all of this again. I will rematch this A, but this has now moved, so the pattern pointer is now over here. I will rematch that and then move over here and find a mismatch there. Okay?
Okay.
That's it.
All right.
All this I didn't have to rematch again. So every time I'll move it, I will only match the last two characters, and I'll be able to move forward.
Okay. Okay.
So earlier I had to match the whole pattern right from the start, and only at the end of that pattern would I find a mismatch. Now I only have to deal with the last 1 or 2 characters. Okay?
Okay.
And you can see that the text pointer never moved back, always going forward. That's the secret for m plus n. Okay. And not only that, it'll find you all occurrences of the text in the pattern. So the secret here is to figure out how much it needs to slide by. So we're going to try and figure that out by looking at some examples. So here's an example from Sedgwick's book. So I'm going to try and see if we could follow this through. This time it's not Ananas. It's actually very similar. It's AB, AB, AC. So think of B as your N and C as your S. Doesn't matter. It's really the same word, right?
Yeah.
And here's the complete state diagram. So now the numbers changed. Instead of doing 1, 2, 3, 4, 5, it starts from 0 and goes to 6. So bear with me. So when you are at 0, it means you have not seen any part of the pattern. Nothing has been matched so far. And when you get to 1, it says 1 character of the ananas has been matched. When you get to 2, the first 2 characters of the word of the pattern ananas have been matched, and so on and so forth. If you ever get here, you've matched all, and you can either stop or keep going. It's up to you. Okay? Now let's see all the things that's going on. So at every point, you could see A, B, or C. And I need to figure out exactly what to do in each of those cases. Of course, there may be more letters in the alphabet, but your state diagram will tell you exactly what to do in each of those cases. So here, the first word letter needs to be an A. So if you only see a B or a C, you're just going to stay there. If you see an A, you get here. If you see more A's, you're going to stay there. If you see a B, you get here. But if you see a C, it's back to square. It's back to your start state. Things like this. You can go and verify that each of these makes sense. The best parts come somewhere here. Say, for instance, you're here. You've got A, B, A, B, A. And now you got another B instead of a C. You're going to go back here, not all the way somewhere there. That's the good part. If you see a, it takes you back here. If you see a C, it takes you forward. Good? If you can figure this out, then the algorithm is not so difficult, and I'll show you what that looks like. But before we do that, we're actually going to see an example. So here is the best part of all of this. When you created this, right? When you created this state diagram, you created it by only looking at the pattern and not at the text. I don't care what the text looks like. This stuff is correct for any text. So therefore, we know the pattern is small. Typically, I can go and create this right at the start. Once I'm ready, it tells me exactly what to do with the text. And I'm going to take the text and use this state diagram to figure out what to do. All right, that's what I'm going to show you next. Here's the general idea. That's my text, okay, up there on the top line. And my pattern, of course, is AB, AB, AC. So text is that long thing. It shows 16 characters. It could be 1600 characters. You don't really care. The pattern is only 6 characters, AB, AB, AC. And I have built that state diagram that I had before by only looking at the pattern. Now you give me a text. So I check the A doesn't match. So I'm still in state 0. A doesn't match, still in state 0, and so on and so forth. So the red things tell you where the mismatch occurred, and the second row tells me what state I'm in. All I did was follow the rules that I had on the previous slide. I didn't do anything different. I just followed these instructions and applied it blindly. And that tells me what state I'm in. If I get to state 6, I can say, oh yeah, I found it. Okay?
At C, Professor?
Yeah.
The index?
At index 7?
Yeah, what does it increment the state 3?
Right. So, right. So it saw the A, B, A, and it's looking for another B, but instead it saw a C. And let's check over here. So A, B, A. So A takes me there. B or C should have taken me to 0. So why did it go to 3 then? That should have been 2. Sorry, that should have been 0. So I think that's a typo. Yeah.
Wait, can you go to the state representation?
Yep. You can see that in state 2, if I see a C, it takes me back to 0.
Wait, when you see that second A, it takes you to 3, right?
Yes. Oh, that's why it's a 3. Oh, you're right. You're right. You're right. So it's a step behind.
Oh, I see. Okay.
So it's in state 3 and sees a C and jumps to 0.
Okay.
Yeah, sorry. Yeah, you're right. So there's no typo there. Okay.
Yeah, then next one's 0.
Yeah. Yeah, so ABA, so the state tells you how many characters have been matched prior to this, right? So if I'm on position 7 and I'm on state 3, then ABA is correct, and I'm looking for the rest of it. Is that clear?
Wait, I'm trying to see. So you're saying the state, basically what the state is, it tells you how many
Yeah.
characters you've matched.
So
the
this
first
is
time
this is where the state is, right? These are the
Okay.
state numbers. Look over here now. Look at number 7. Okay? I'm on state 3. That tells me that 3 of my characters are correctly matched prior to this. Prior to that C is ABA.
Oh.
ABA is the 3 characters of the pattern, and they've been matched.
Oh, okay.
Okay?
So, okay, if that's the case, so the first time, so you see A first, then you see B, so why wouldn't it increment the state to 2 when you see B?
Where?
I'm trying to see, okay, so like at, I guess at column 4,
Yeah.
like, yeah, column 4.
You're
so
still an
when
A,
you encounter
yeah.
an A, so let me see, so that's a 1.
Yeah.
I guess because you've matched 1 so far, right?
Because you matched the first A. That's correct.
Right, then you see B, so but it still stays 1.
It's turning to 2 here. So it sees the B and changes the state to 2.
Oh,
And
so
then-
I guess it changes the state
right.
like at the next.
So
Huh.
perhaps they should have put the state row prior to the character here. This says if in state 1 I see a B, I'm going to go to state 2.
Huh. Okay.
If in state 2 I see an A, I'm going to go to state 3.
Oh.
If in state 3 I see a C, I'm going to go to state 0. And that's exactly my instructions from the state diagram.
Oh.
Okay?
Yeah, I think I'm following a little.
Yeah,
more.
it's a little
Yeah.
little off there. You just have to read it correctly.
I guess so it increments the state like in the next one, like after
Yes.
it finds a match.
Yes,
Oh,
exactly.
Okay.
Now, all this other stuff here, right? This is what's happening with the pattern. That's the sliding window of the pattern. Now, the gray stuff is stuff that is not matched currently. The black stuff is things that are perfectly matched, and the red stuff are things that are mismatches. Okay? So, the A mismatched right at the start. Then again, you slid it over, and again the A mismatched. Again, the A mismatched. Now the A matches, that's why it's black in color, right? Then you look for the B, and the B matches, B doesn't match, and so therefore it's red in color. So in each case, you'll see that when there is a red colored character, it'll slide over on the next row. Clear?
Okay.
Yeah.
Can we discuss that match and mismatch logic? That's referring to the
Here?
this table, right? Yeah.
Yeah, so this is saying the character at position I in the text and the character J at position, character at position J in the pattern. It's checking those two and figuring out what it does. Now, in order to figure out what to do, it has to change the state, and the state is given by the DFA. DFA stands for deterministic finite state automaton. Anyways, all that is not necessary. So this is the lookup table for that strange thing we had that says if this is my current state, and if if this is the character I see, and if this is the state I'm in, it'll tell me what to do next, where to go next. That's what it is. Yeah. And remember, the J is the same as both the state as well as what character you're in the pattern, right? That's the character you're going to look at again. If the state is 3, then I'm looking at the third character. Oh, sorry, I've already matched 3 characters, so I'm actually looking at the 4th character, but the index would be 3 because I'm starting all indices from 0, right? Does this make sense?
Yeah.
Okay, we still haven't quite gotten everything together. we haven't figured out how to build that diagram. That's what's next. So the whole thing hinges on us having this diagram done. This diagram is the same as the table, right? I can put it in the form of a table. It's not a big deal. In fact, that table is over there. That's the DFA table. That tells me, and that table should match this. You can see here, if I'm in state 3 and I see a B, then I should go to 4. If I'm in state 3 and I see a B, I should go to 4. Let me point this here. If I'm in state 3 and I see a B, I should go to 4. If I'm in 4 and I see an A, I should go to 5. If I'm in 5 and I see a C, I should go to 6. These are the standard ones. The other numbers tell you where to go if that didn't work out. So the others are all because of mismatches. But not all mismatches go back to 0. And that's the good part. Even if it goes to 0, it'll slide everything over until so that you never have to rematch things you already correctly matched, except the current character. Okay?
Okay.
That's the trick. So we still need to figure out how the heck we're going to construct this table or this diagram. If we can do it, then everything is going to go very fast and very smooth. Clear? Okay. So let's now see how to build that diagram. Well, we start with nothing. So we start with state 0. That's our start state. We know what our first character should be because we know the first character in the pattern. Remember, we're only looking at the pattern. We're not looking at the text. So we're looking at the short pattern, and we're going to figure out this diagram. If we are at state 0, if the first character is the first character in the pattern, which is A, then I'll go to state 1. That part is easy. If I see anything else, I just stay there. Easy. This part is easy. Good. So we're done with that. Next, we'll come down here. We'll have to figure out what all things could happen at state 1. Then we'll do state 2. Then we'll do state 3 and finish up. So what happens in state 1? I know that the second character is a B in the pattern. So a B will take me to state 2. Everything else, I have to kind of figure out where to go. Over here, if you see an A, it stays there. If you see a C, it goes back to 0. Now, how you figure that out is part of the magic. Okay. So let's see what this strange comment is. I can't remember this now. Right, so clearly over here you'll go to J plus 1 if you see the B. So you'll go from 1 to 2 if you see the correct character. Right? The second character is a B, so therefore that'll take you to state 2. That's the easy one. So that's the first statement here. And then what is this? Pum. Yeah, how do you figure out the red parts? Let's see if there are clues later on. So then you'll go and do the state 2, and this part also is going to be easy. A will take you here, anything else will take you somewhere else.
Professor, that copy DFA X, DFA J,
Yeah.
it's taking that first column where the X is pointed at and copying it to the row B.
Yeah. Looks like it, right? So we are at state J. Yeah. Don't quite see it yet, but it will. Let's move forward and hopefully figure that out. Here is the rest of it, but it still doesn't help us, right? So you can see that this diagram is being built incrementally. You do it one step at a time, which is the same as saying we're building one column at a time of that matrix, right? Because each column is for a specific state. And you're right, it says something about copying. So let's see if we can figure this out. It says copy X to DFAJ wherever you can, and then you improve it. It looks to me like in each one you're copying the character that matches. So how did they figure that out? Let's see if we can see it over here. So so that seems like this is what's happening. It seems to me you are, in order to figure out this column, you're copying the B column from here, and then this is the only one that'll change because the fourth character was a B. So if you see a B, then it should change this to a 4. Everything else is exactly the same as this. But why did it copy that column? I haven't quite figured out. Hopefully it'll come. Okay. Then over here, again, this A matches this A, so this just copies this over, and the only thing that needs to change is the first row, because it'll go from 4 to 5 over here. Is that clear? So let's see what happens here. Why did it use this guy here?
What was their logic for implementing X? I think it was in the slide before this.
I have the pseudocode here. Let's see if that helps us.
Professor, sorry, I just got a little lost in the DFA. So DFA, like, can you explain that again? Like,
DFA is the diagram.
Oh, DFA is the whole,
yeah.
Okay.
Okay, so this is our algorithm. It only takes the pattern as your in order to figure out, and this is supposed to figure out the DFA. The DFA is simply the matrix description of the diagram that we drew. So there are some initializations. So that just creates the DFA here, right? So the DFA is created here. This is looking at the first character of the pattern and it's saying if you see that first character, you should go to state 1. So this is how it initializes. After this, it just goes and takes care of the rest of the pattern. Now, over here, J starts at 1 because you've already taken care of 0, right? Because you've taken care of the 0 column. So J starts at 1. X is the strange thing that it's going to copy over. That's initialized to 0. And then after that, it just says, have you reached the end of the pattern? And otherwise, keep incrementing it. Then it says, there is another character C that looks at all the letters of the alphabet, right? So for every letter of the alphabet, you have to figure this out. And the way you figure this out is you simply copy over the column X. That's what it seems like. And initialize that to 0. So you're just going to copy whatever that X is. We have to figure out what X is going to be, and that's given over here. That's the secret sauce that we haven't quite figured out, but it'll come. And then there is one thing that's going to be changed from the previous column, and that is if you see the correct character, then you should go to J plus 1. That part is clear. Now, what the heck is this? Right. So we copied it over from the X column over there. Whatever we figured out over there in terms of where we should go with X, that's going to be a new X. Little tricky, isn't it? Yeah, let's try and figure this out. Okay, let's look over here. X was here, which is fine. That's how the algorithm played out. Okay, so X was here. So when you come to this column, you're simply going to copy that column over, and then you're going to change the C because that's the last character of the pattern, right? So the question is, what happens to X at this point? X is going to be whatever from here, whatever it says you should do with C, that's what should happen here. That's what your new X should be. It says your new X should be whatever that column, the current column of X, tells you should do at when you see X. Is it? No, when you see the current character. Sorry. Whatever it said over there you should do with that current character, that's what you should do now. So that means when you get here, your new X is going to be whatever this guy said you should do upon seeing a C, which would be a 0. Now let's see if we can figure that out from here, right? Okay, so we have X over here, so we copied it. We fixed the first row because that character was an A, right? That part is fine. Now we have to figure out what the new value of X is. The new value of X is whatever this column tells us we should do when we see an A. And that, it says go to 3, so that's why X is 3. Because if you were there and if you see an A, it tells you how much of it has been matched at that point. That's what you should carry over. So this is the small tricky part, but now it's making sense. We can now check that step as well, if you want. When you did that, you first copied 1 to 0 over here, and then since the character was B, you're changing the middle number to 4, and then your new X should be whatever this column said we should do when we see a B, which would be a 2. And so X becomes 2. Now, what was the logic there? Let's try and understand the logic. The logic was that so in order to understand the logic, we need to understand what X really means, right? What does X mean? Let's see if we can figure that out. X tells us so when I take my pattern, here's my pattern, right? And let's say that I have matched everything until here. There's more of the pattern here, but let's say I've matched everything until here, and I am now looking at the next character. Now, if I try to match my pattern with itself, what would happen? That means that if I try to match my pattern with its, so let's say I do a pattern match of my pattern with the pattern. Okay? Then you want to understand what it looks like, which means it's going to sit like this. You want to know what is the largest prefix here that matches with everything you've seen so far. If I know that, then I can slide it over by that. That's what I need. So X actually tells me what this position is. And so it reflects how much to slide it over by. Does that make sense?
Oh, so basically you're saying so our X is the part like where we don't match anymore. So
X is exactly the things that would have matched if I were to take the first X characters and sit it here. If I have that, then I'm great because all that has already been matched.
Ah, okay.
Right?
Yeah.
So now I can go to state X.
Yeah.
That's the plan. So X is a strange thing that tells us what part I could reuse if there were a mismatch here.
And that explains why it's delayed, and why.
Why you want to go from X to wherever that next state is. Yeah.
Okay.
Yeah.
Wow.
So that's the trickiest part in this.
Yeah.
The rest of the picture is not so challenging. This is the part that you have to be some kind of a genius to figure that out. But the rest of it is really, it's just following your nose in some sense, right? So also what this tells you is that this code is just out of the world, okay? And it was designed by 3 people, Knuth, Morris, and Pratt. That's why it's called KMP. And basically, if you're in a competition, you just take this code and use it to build your finite state machine. And then once you do that, the rest of it is actually quite simple. This is the search part where it takes whatever text you give me, and it uses the DFA that I created there and simply does my for loop, which is scanning the text from left to right. So here it says for I equals 0 all the way up to the end of the text, but it's also possible that I'll end, I may reach the end of the pattern, And then this simply says use the DFA to go wherever it tells you to go. Don't do anything different. Just follow the instructions. If at any point you reach M, which is the end of the pattern, report it as something that's matched. Depending on whether you want one match or all matches, you would have to modify this code. Okay? If you reach the end of the text, that means you haven't found it. That's it. And suddenly, your algorithm, instead of being big O of m times n, is now guaranteed to run in m plus n. Okay? This is pretty straightforward, right?
Yeah.
There are some details here that are messy. You are checking whether you hit the end of the text or the pattern. If you hit the end of the pattern, then you found a match. If you hit the end of the text, then you failed. So this will only report one hit. But you could put this if statement inside here, inside the for loop, so that when it hits it, it tells you even where to go for the last state, and then continues. Over here, in fact, when we did this diagram, we did not bother with the state 6. You would have to figure that out as well in order to keep it going and continue with finding all the hits. So it needs one more step. You have to figure out column 6. In the simple case where we have to report only one hit, state 6 is a dead state, halt state. Once you get there, you can scream and say, I found it, and stop. But if you want to keep going, you have to add that column 6 to the DFA. Okay? That's it. This is your KMP algorithm. I just told you how to modify it if you want to find all hits. Now, it gets very, very hard. This algorithm is really not that useful if you want to find a match with just one mismatch. It's just nasty. Doesn't work very well. Okay? So approximate searches do not work here. It's not even funny, because trying to figure out what to do with the state diagram is just too crazy. So we need fresh techniques for harder string problems. So this KMP algorithm, as fabulous as it might be, it's not enough to solve harder string problems. Okay? Yeah?
For a naive solution to the harder string search, can we, let's say our pattern is a length 5.
Yeah.
Can we get all length 5 substrings from the text and then do the edit distance?
You can't, because even to find the match, so you can generate all your edit 1 or edit 2 distances and then do a search with those. That's possible. But you can't find the match and then look for the edit distance, because the match itself doesn't happen. They all have mistakes.
So can we just drop the match and just look
Yeah.
at the?
That's completely reasonable to do. So you take your pattern, edit it with all possible edits, and then for each one you run it again, right?
But there's a better solution?
Yeah. Okay.
Yeah, Professor. Actually, I still haven't quite wrapped my head around why the solution we just came up with doesn't quite work for everything.
Yeah, that's okay. That's fine.
Explain tomorrow.
Yeah.
Review.
Unfortunately, I may not be able to come tomorrow, but okay.
We'll have it recorded then.
Sure, okay, yeah.
Yeah.
'Cause I know we're gonna-
So we're going to look at some other solutions. By the way, there's something else called Boyer-Moore, which turns out to be slightly faster than KMP in some cases. Instead of doing it the way they're doing, instead of looking at the pattern left to right, they look at the pattern right to left and do amazing things. So anyways, there are so many ideas that people have come up with, it'll just boggle your mind. And they're all not that fancy. They're all simple ideas that says, they started with things like what we did here, where we said, why are we looking at these A's again? We knew it was all A's, right? So how can we use that to speed up things? Things like that. So they came up with ideas, and it turns out that the amazing stuff happened. In Boyer-Moore's algorithm, if I start my scan from the right, I see that this is a B and it doesn't match. And B is nowhere to be found here. So therefore, I can just move this all the way. Did I get that right? No. Sorry, I made a mistake. So Boyer-Moore is useful, for instance, if this is all A's, and this here is a B. Okay. So now, this is all A's. This is a mismatch. Why am I wasting time? There are no B's here. Let me just move forward. So with just one character match, I can move this over to here. Right? So things like that. So there are crazy ideas that they've figured out how to do really, really efficiently. That was one. Okay? Let me show you one more. This one uses something called a trie. Now, to start with, it's going to look somewhat silly. Let's say this example is to build a dictionary. I have these words, big, bigger, bill, good, and gosh, and I want to build a dictionary. What's a dictionary? Dictionary is somewhere where I can search, right? So here's how I do this. I take the word big and put it one letter at a time and end it with a leaf. Then I take the word bigger, which uses part of big but then goes off in another direction and comes down here to bigger. Then I have bill, which uses part of big but goes off in a different direction after the BI. So it's one letter at a time. But this tree tells me exactly what to do. It says if it's a B, take that path. If it's an I next, take that path, and so on. If you ever reach one of these leaves, you can say I found the word. So here, we're not just looking at one text, we're looking at a collection of words, a dictionary. So yet another different example, right? So it's not one long text, but it's a collection of smaller words. And it seems that this approach could be better. Let's see, is it? So the trie approach builds a dictionary in this manner. It just looks very inefficient overall because you're building one character at a time. However, there are ways to improve this. You can build what are called as compact suffix tries. So a suffix trie is actually something strange. If I want to use the word, if let's say I want to, if I have the word Google, by the way, Google is 1 followed by 100 zeros. I could take, in order to do lots of interesting problems, here's one approach that people figured out. They said, take the word Google, take every possible suffix of the word. Suffix is whatever is towards the end, and put them into a dictionary. So I have just the $sign, then just the L sign, then just OL, then what's the next word? GOL, GOL, then OGOL, and then OOGOL, and then Google. So every possible suffix is now put in this dictionary. This turns out to be really useful because now if you give me a pattern and say, hey, can you look for the word OOG? It turns out if it's there, I can find it here by simply following OOG. So O goes there, G comes here. If you get here, then I've found it. It's there somewhere in the dictionary. And in fact, I can even put in pointers to tell me exactly where it is. Okay? So that means I can essentially do what KMP algorithm did, where I can search for patterns in a text, but this time I am actually processing the text and building this thing.
Professor, you said go to the tree from the pattern or go to the tree from the text?
Go to the try from the text. This time I'm not doing pattern.
Okay.
So for every word in the dictionary, I'm going to take all its suffixes, build this nasty looking structure, but then once I do this, I can now search for any pattern you want. That's sometimes useful because often your dictionary is static, is given to you prior, and you can process it, and you have lots of people asking queries. In other problems, you are, especially in Microsoft Word, when you're typing, you're looking for a word, the text is always changing, and the word you might be searching for is ad hoc, it comes up quickly, and you may search for the same word many, many times. So these applications are slightly different. So this is a slightly different application where you want to build a dictionary. And you still want to be able to search for substrings of the word. So this suffix try turns out to be quite valuable. Now you can make this compact by taking any long path like this that doesn't have branches and just compress it. That turns out to make life a lot easier, and it turns out to be quite efficient. Okay? And people know how to build this quickly, in fact in linear time. And yeah. So I won't have time to go through this because our time is up already and I have another meeting soon. So we can talk about these suffix. So from suffix tries, you can go to suffix trees. From suffix trees, you can go to suffix arrays. Each one is better than the previous one, and they do pretty amazing things. And they can even do approximate searches. I mean, it's quite powerful. So we will try to understand some of the theory here next semester, but you can also go and directly use the code. What you need to write down for yourself, understand for yourself, is what is the black box description of each of these? When are they useful? When are they not? What can it do? What is the input? What is the output? Okay. Once you have that, you can figure this out. So the suffix trees can be built in linear time, and the matching is very fast. From there, we can also build something called suffix arrays. From there, we can also do something called Burrows-Wheeler transform coding, which is another amazing algorithm. So this string field is full of just great algorithms. But what you need to know is what are the black box descriptions so that you can just use them for coding other applications. Yeah, I'm actually going to stop here because there's quite a bit of stuff that I could talk about.
Can you send us the slide?
Yeah. Here's another interesting question. What if I want to find the number of occurrences of a pattern in a text in some part of the text? Or what if I want to find the first occurrence, or what if I want to find the third occurrence, and things like this. So I can make hard problems, and many of these suffix arrays are actually quite reasonably good at it. Then there are something called wavelet trees, and so on. So yeah, we can go on for a long time. This is a entire semester worth of stuff. But the field is fascinating, and what we thought, we could code in 2 for loops. These people have spent their entire lifetime trying to figure out how to improve on this. Okay? So fascinating stuff.